also had 182 UGF. This alternate on
Okay, very good. So, as I mentioned, we will have our usual problem section. I call it special in the sense that we don't have any of this. So, we'll just have it as an opportunity to have a discussion. All right? So I'll be available from 10:15, 10:30. All righty. Everyone has their assignment, right, for the final project? And anyone have any questions about it? Well, if questions arise, you'll email me. So what I would like from you, what your assignment is to come up with just a little proposal, a few sentences, so what you're going to do for your final project. I'll prove it. All right? All right? Very good. All right, so today I hope we'll really be able to tie up this whole idea of the Hanbury-Brown twist experiment and the related, very important question of classical versus non-classical light. That's really where we're headed in our discussion here. Hopefully that will all become more apparent what I mean by that by the end of the class. All right. So let us firstly just once again recall what we're talking about when we think about the classical description of optical coherence. Okay. So what that means is that the classical wave amplitude, complex amplitude, is treated as a classical statistically random variable, generally, okay? And so there's some probability distribution of the complex amplitudes. For example, if we have natural light, then we have this kind of Gaussian distribution of the complex, of the phasors, okay? So this is over the average. So such light, as we discussed, has large fluctuations. For example, in the intensity. The intensity coming out of this light bulb is not very constant intensity. At any point in time, we can look at what the intensity is, but if we were to put it on a photodiode, we would see it was fluctuating all over the place. Okay. So if we take that kind of light, for example, and put it on, do a intensity correlation experiment, which is the Hanbury-Brown twist paradigm. So we correlate the intensity at one time with the intensity at a different time. And that's done here by just splitting the intensity up and looking at the correlation between the intensities at two different chunks of time. Then classically, what that is the average over the probability distribution, okay, of the product of the intensities. And I just wrote that out in terms of the average over the probability distribution. So each one of these things, of course, is a function now of all these mode amplitudes. I'm not writing that out. That's what that average means, that you average over that probability distribution. That, although we didn't show it in detail, I argued just by the force of my voice that correlation function has this form if when the statistics of the probability of the complex amplitudes and phasors is Gaussian, that you end up with the product of all the two-point correlation functions. Okay? And so what that tells us is that the correlation between the intensity at two different times is equal to the square of the intensity. Of course, all of this at the moment is discussed in the context of so-called stationary statistics, which is saying the statistics don't change with time. So the mean intensity is independent of time. That's why it's written this way. Plus this term, which is nothing more than the square of the two-time amplitude correlation function for the complex amplitudes. And so the intensity correlation function has this form, right? Which says that that the correlation function will fall off, in this case, under the assumption that of the particular kind of spectrum that we had. So this is not a general expression. This is about thermal light or natural light, certain coherence time. I use the term thermal light. I haven't actually discussed what I mean by thermal light yet. I'll talk about that in a moment. Falls off with that correlation function. Okay? And I just want to emphasize here that this difference, the difference between this function, which is what I'm plotting, and this, is nothing more than the correlation in the fluctuation in the intensity. Okay? So I'm looking at, if I look at how the fluctuation in the intensity relative to, this is the difference between the intensity at that time and the mean intensity, how that is correlated with the fluctuation in intensity, or the deviation in the intensity at some other time, say t equals 0, average over that. That's just this function. That's right? Is that clear? You multiply that out. That's what it is. So what we're measuring in the Hamburg-Brown and Twist experiment is the correlation in the intensity fluctuations. And you can use that to measure the coherence time. So if you think about it from that perspective, from a classical wave perspective, that makes sense. If your time is short compared to the coherence time, well then the intensity is correlated with itself very well. But at times, if you're looking at the intensity at two times that are very big, then there's fluctuations are uncorrelated with one another. So that's no big deal. But as I said, this, from the point of view of, if you wanted to think about this and understand this kind of experiment from the point of view of quantum, then that caused a lot of confusion back in the day in terms of what was going on in terms of photons. So let us again discuss that. So, of course, when we're talking about the quantum description, the fully quantum description, then if we're talking about the quantum field, there are two aspects of this. There are waves and there are particles. And all of this gets very intertwined and to some degree confused. Because in some sense we have two kinds of waves. We have the waves that we think about as the wave function, the probability waves, from which we talk about quantum mechanics, and then we have waves which we're talking about as the electric wave that's being radiated, right, which is an element of reality of sorts. And that's part of what gets confusing here. So in order to attack this problem, as I discussed, we follow in Glauber's footsteps and think about a fully quantum mechanical description of the whole process. So the first thing is what's going on is to think about photodetectors. And in particular, what we're talking about here are photon counters. So if I have some detector which is shine light on this and it counts photons, then that photon counting in some time interval, as we discussed, is proportional to the expectation value of the intensity operator given a atom at some point in some time. Where the intensity operator here, I mean, it's not really the unit of intensity here. I'm writing, I mean, units float around here in uncontrolled ways. I'm going to try to put them in when necessary. Is this operator. Now, this order of having the positive frequency component to the right and the negative frequency component to the left is extremely important. Okay? This is what's called normal order. Well, this is a term that we'll use over and over again in our next semester of the course when we talk about non-classical and more generality. But what it's basically saying, normal order means, remember, of course, this is proportional to the annihilation operator, and this thing is proportional to creation operators, right? I mean, for each mode. So normal order says all the creation operators are to the left and all the annihilation operators are to the right. That came out of the derivation of this, that the photon counting was important to this, because, well, the photo counter absorbed a photon, right? So that's how it came out. And this expectation value is taken over, this is equal to the trace of this operator with whatever the state of the field is. Could be a pure state, could be a mixed state, I don't care. So that's what a photon counter is doing, in some sense, okay? So you can think about this is like the number operator, right? So this is like measuring the number. The photon current you see at any time is measuring the number of photons. It's counting how many, okay? Yeah?
Is that why the order is like that?
Well, the order is like that because it came out that way. And so that is to say, we derived it. If you go back to the previous lecture, we said that, you know, the rate of, that this thing depended on, you know, some initial state for the field and some final state for the field and the interaction Hamiltonian. So we had, you know, the field in some initial state, then we had the ground state, and then we had the field in some final state, and the atom excited. This is what we started with. We didn't a priori say, it's the number operator, it's got to be the number operator. No, that's not what we said. What we said is there's a rate of absorption. This interaction Hamiltonian was E dot E, where E has both the positive and negative frequency components. But because we said that this has to go from the ground to excited state in the rotating wave approximation, this only had the E plus term and not the E minus. And then when we squared it, we got that. Yeah?
So this intensity operator is a function of space and time.
generally.
When I sometimes read about POEMs describing photon counting, it's usually a projection operator onto a Fock state. Is that just lazier, or is that a different measurement, or is that related to this at all?
Well, that's a little bit of a tricky business. As I mentioned at one point before, a photon counter is not actually a projective measurement, right? What is a projective measurement in quantum mechanics? Any thoughts about what does that mean, a projective measurement?
It takes it from being in a superposition of something to
An eigenstate, right? So it's the usual, first thing you learn of what a measurement is in quantum mechanics. You measure an observable, you get an eigenvalue. If you get that eigenvalue, the system collapses onto the eigenvector associated with that observable, then the eigenvalue that is measured. But that's not what a photon counter does. Photon counter absorbs the photons. They're not into that. So, but what is true is that the photon counters, the photoelectrons that you see, or the little spikes in current that your photodetector gives for each photon, has the same statistics as the probability of seeing n photons in that time interval. Okay, so if you were to ask, as we will, and we'll see this, right? So this thing is in some sense measuring photon number, but it's not doing it in a projective way, the way you just described. So in some sense, it's a lazy man's way of as you said, writing, I have a projector onto a number state. It's not really what's happening.
Okay, cool.
All right, good. So, let me remind myself what I wanted to say. Oh, yeah. Okay, fine. So that's the quantum theory of the photodetection. And so, for example, suppose the field was in a pure state. Let's just suppose that be true. And suppose that state was, in fact, a coherent state. Well, if that's true, this state is an eigenstate of the positive frequency component, right? They're eigenstates of the annihilation operator. So this thing, when it hits it, it just gives me the classical amplitude, associated with that set of mode amplitudes at that position in time. That doesn't matter. So this recovers the classical description if my state is a coherent state, right? It's exactly what I would have classically for the intensity, right? It would be the square of the complex amplitude. Because you take that expectation value, and on the opposite side, the E minus is just the bra, right? So it would recover. Moreover, if my state is a statistical mixture, a classical statistical mixture of coherent states, well, the same thing is true, right? So if my state is some statistical mixture, I'll just write it like this. For all the modes, there's some probability distribution of having that. So this is the quantum mechanical state associated with a light that's coming out of a light bulb. It's a statistical mixture of coherent states. I don't know what the classical amplitude is, so I have to average over that, where this is whatever distribution I like. For example, the Gaussian distribution that we just wrote down. So this is the description, this is what we would call, say, natural light, where this is Gaussian. And in fact, this now has this form where nk is that for each coherent state, right? All right, so that says that the Glauber theory of photodetection, this is average over the distribution, could just obviously recover what we just did, right? I mean, if I look, for example, at the Mach-Zehnder interferometer, then the linear transformation is such, I put in some input field at position R and T. And I have some output field at position out and T. That this guy is nothing more than the linear superposition of those guys. Right? And again, if we suppress this, this is all, say, the positive frequency component. If I suppress the dependence on position, we're at some fixed position. And I look now at, say, the output intensity. I look at the expectation value of that. Right? That's equal to E minus out T, T plus out T. Suppressing all of it. And again, if I assume stationary statistics of the state, I don't have to, but if I do that, then this is equal to 1/2 times average I plus twice, what have I already put the chip there, is the real part of E minus tau with E plus F0, where tau is T2 minus T1 over, yeah, it's just the difference in the times of the two paths. Okay. So again, if this were a coherent state, these just get replaced by the coherent amplitudes, and it's exactly what I have from the classical description. And if the state was of this form, well, it would be, again, exactly the same thing that we had from the classical amplitudes. As we discussed, a bit of notation here. This thing is known as G1 of tau. Let me give you some notational definitions here. generally, one defines G1 as a function of R1T1 and R2T2 as the expectation value of E minus at R1T1 with E plus at R2T2. That's the most general definition. You will often see this as a function of one thing. You'll see people always write G2 of tau or G1 of tau, right, Nick? You see that? We were talking about that the other day. So what does that mean? When I write G, so if I'm thinking about temporal coherence, and I have stationary statistics, then often you will see this written as just a function G1. So this is at the same time, and then I'll look at it as a function of T1 minus T2, where G1, where this would then be equal to, I forget about the spatial dependence, and there are two times like that, but it's not a function of the individual times. It's only a function of the time difference. And so, for example, you will see this, then if it doesn't depend on the time difference, I'll call this G2 of tau, where this is E minus, E plus. Okay, so you'll see that. Moreover, one defines a so-called normalized correlation function, little g, G1 of R1, T1, and R2, T2 is equal to G1, R1, T1, R2, T2 divided by the square root of G1, R1, T1 with itself, R1, T1, and then again with the other argument. So that's the most general definition of the so-called normalized correlation functions. And then if I have stationary statistics, then we have a little G1 of tau, which is equal to big G1 of tau divided by the square root of G1 of 0 with itself. Because of course, if it's the same, T1 equals itself in both of these guys. So this is equal to G1 of tau divided by G1 of 0, magnitude of that, whatever that is. And that is what? G1 of 0. Tau is 0. What is that?
It's the intensity.
That's the intensity. So this is equal to G1 over the intensity. All right?
What would the normalized tell you? Just
Well, here's what it tells you. So we'll see how
Okay,
it's going to come out. So if I look at it here, this is, of course, the average of the intensity operating. This is equal to 1/2 the intensity divided by 1 plus G1 tau. So that's what it tells you.
okay, and so it goes from 0 to 1, or?
Yeah.
Okay, cool.
In fact, well, it's the real part, excuse me, in this case. Now, what we just did here is, in some sense, seems completely brain dead. I mean, what was the point of this? We had the classical theory, we dressed it all up with quantum operators, but then at the end of the day, we reverted back to the classical amplitudes, because we just replaced the quantum operators back with the complex amplitudes. And we got exactly the same thing that we had classically. Well, that's maybe in some sense satisfying. It says within the quantum mechanical formalism, there is a description of this kind of classical thing. Obviously, what we want to do is go beyond that to states that don't have this kind of description. Yes, sir.
If we had light that was not Gaussianly distributed the way we are talking about it, but was in the coherent state,
Yeah.
would we still get the same, and we looked at the intensity correlations?
We wouldn't get the same function, no. I mean, as we were going to see a little bit later in the lecture, there are certain bounds that are satisfied, certain inequalities that are satisfied, that are demanded by the fact that my state has this form. So the Gaussian is a specific case. It's a specific case that's associated with the central limit theorem, if you like, and something that's more like what we were, as we're going to see in a little bit, thermal equilibrium. Okay, but that's a specific case. Nonetheless, what's true here is that if this is an honest-to-God probability distribution, that's to say this is some number that's always positive and typically normalized between 0 and 1, then that, as we will see, will set certain bounds and conditions on what we could see. A state, if we violate those bounds, then what we would say is that the light is non-classical. It cannot be described in terms of a statistical mixture of complex amplitudes, but something more akin to a superposition. That's where we're headed. All right, now, as we said just a moment ago, the quantum field, we can describe it in terms of waves, or we can describe it in terms of particles. What we just did is the kind of quantum wave description. We said that the states that are like that have to do with the wave degrees of freedom are coherent states. But we should also be able to describe this in terms of particles and interference of potential histories that the particles could have gone through in order to achieve a certain detection outcome. Now, of course, we know it. We've seen that. We know that. In fact, as we described, even if I had a single photon, it would show the same kind of interference that the coherent states do. So how do we think about this in terms of photons rather than complex amplitudes? Well, let's think about this state. Let's come back over here. This is a quantum mechanical state. It is written in terms of coherent states. But I can also write it, if I want, in the basis of numbers of photons. Because I can express it in any basis I like. What does that look like in the photon number basis? Well, let's think about that for a moment. So let's think about a single mode. So my rho here is the integral over the real and imaginary parts of that thing times e to the minus alpha squared over the average pi and alpha alpha. Now, you remember that alpha itself can be expressed in terms of the numbers, right? And that is equal to alpha to the n over the square root of n factorial e to the minus alpha squared over 2 n. So you plug that in, you're going to get two sums, sum over n prime. You do the integral. This will be a homework problem someday. And you find the following. This is equal to the sum over n equal to your infinity of the following. Average n to the n over average n plus 1 to the n. So this state, which is a Gaussian mixture of coherent states with this particular probability distribution, is itself a statistical mixture of number states. Okay. Now, do you recognize this distribution?
Just wondering.
Huh? Take a guess.
Binomial?
Yeah, it's a fine guess. I have to guess. What the heck? This is a Bose-Einstein distribution.
Oh.
Everyone's got to study for the prelims. This is a Bose-Einstein distribution. What is a Bose-Einstein distribution? Bose-Einstein distribution is the distribution of possible excitations of a harmonic oscillator when the harmonic oscillator is in thermal equilibrium. So let me remind you about that. The first one. So, recall, if I have a simple harmonic oscillator in thermal equilibrium, and so then I can ask the probability of seeing n excitations of that harmonic oscillator is equal to the energy, N bar omega, divided by the Boltzmann constant over the partition function, right? And if you do that, what you find is that the mean excitation is equal to that, which is the Planck result, right? And if you put in the partition function, right, you get this. Okay? So, what that says is something interesting, which maybe you didn't know. That a harmonic oscillator in thermal equilibrium, well, I can think about it quantum mechanically as having a thermal distribution of a certain number probability to be in the nth level of the harmonic oscillator. That's one way to think about it. But or equivalently, I can think about it as a oscillating pendulum or a simple harmonic oscillator whose complex amplitude is randomly distributed. Randomly distributed according to a Gaussian distribution with an RMS of possible extents that have to do with the mean excitation number, which is of course dependent on the temperature. Okay? So this is what we call the continuous variable description, and this is the discrete variable description. Description in terms of waves, the description in terms of particles. Okay. Now, you can do the math for yourself and ask the following question. What is the uncertainty in the number of excitations? This is not an eigenstate of a number operator, right? It's got a probability distribution of different numbers. What's the fluctuation then? Well, you could do it, the math. You could do it either way. I could do it and take the this is equal to the mean n squared minus the mean of n squared. I could do it in this basis or that basis. And what you find is the following. This is equal to the mean n plus the mean of n squared. Okay. Hold on a second. Something looks wrong and I've got myself confused at that point. Sorry. Oh, okay. Right, okay, sorry. All right, back with you. So, yes, this is correct. And so one thing that we see here is that if I look at, for example, the difference between n squared and n, quantity squared, is it right? Jeez. I get myself so confused here. sense to me, so I'll come back to it. But I'll just leave this alone for the moment. Okay, sorry. All right, so, fine. This is a thermostat. We'll come back to this in a moment. But now, what does this mean in terms of our description of the Mach blender? In terms of now thinking about this in terms of the thermal state. So let's come back to this expression for a moment, okay? So what we call natural light here is also sometimes called thermal light. Now, I should make just a slight note on this term, what we mean by thermal in terms of temperature. What is true is that the light coming out of this light bulb has a statistical distribution of photon numbers, which is the Bose-Einstein distribution in any mode. Moreover, its complex amplitudes are Gaussian, has this Gaussian noise. That is true. But the question of temperature is a little bit of a fudge. I mean, what we have here is a multi-mode. This was for a single mode. This is one of the modes. What we have in our description of the natural light here, the state of the field, is a tensor product of the state for each mode. Right? Each one is statistically independent from all others. And so this is equal to the sum, the product over all modes. A sum for each mode has its own distribution. Right? That's the product of those. And now, of course, what is this? Well, that depends on the spectrum, right? The question is, how many photons are there on average in a given mode? If I take this light and I say put it through some kind of narrowband filter, so I have some kind of spectral filter that takes only light, this white light, and filters it out to some small bandwidth around red. Okay? Then the mean number of photons there would have some distribution dependent on the spectral distribution of the filter. If the filter, say, is Lorentzian, then I might say this is equal to the mean, this is the total number of photons divided by times some spectral bandwidth. So there's some gamma coherence time. So this would, for omega sub k. So this would say that I have some distribution of photons centered around some number here. So that's the mean filter, and where gamma sub c is 1 over the coherence. Okay. So the spectral distribution here sets the number of photons. I could define an effective temperature for that if I wanted to, by just setting that equal to the Planck. So there's some black body that would have exactly that. mean number of photons. But that's what we mean when we say thermal state. Okay. All right, so now let's look back at this guy. My total intensity is equal to, well, there's the sum over all the modes. There's some factors here, doesn't really matter, something h bar omega square root omega k prime, expectation value. Right, that's all I got, right? And what is this for a thermal state? We have the thing I just erased, product of over all the modes. Well, this is going to be equal to the sum over, the probability distributions, but then I have nk it's diagonal in the number basis, right? This thing is diagonal, which means it can't, there's no, if every term has exactly the same number of photons, I cannot have off-diagonal terms between two different number of photons, because it's diagonal in the number basis. So this thing is equal to the mean number of photons, delta k prime. Okay? So this is equal to the sum h bar omega k with some constant out front. Right? Which is what you expect. It's, there's something that has really a rate and an area, right? So this is like the total, and this is approximately, if it's this narrow band thing, h, some constant times h bar omega naught times the total number of photons. That's what it would be if this thing is sufficiently narrow band. What about the two-time correlation function, g1 of tau? That's that, right? Well, it's the same kind of thing here, except this thing is going to be the sum, whatever those constants are, but then I'm going to have e to the I omega k tau, right, over here. And again, I get the same thing as before. So this thing is the same as we had before. And so what I end up with is this is going to be equal to the sum over modes, some constant h bar omega k, the mean number of photons times e to the minus omega k tau. Okay. And again, if this is narrow band enough, so I can bring this outside at all approximately omega naught, then this is really approximately equal to that, which is what we call, this is the power spectrum, this is the Fourier transform of the power spectrum. It's the Fourier transform of the number of photons in each frequency mode. So that's another thing I want to once again re-emphasize. A Mach-Zehnder interferometer does nothing more than measure the spectrum. So if I have a coherent pulse that has a certain spectrum, and I have white light that I put through the same spectral filter, and I put it on a Mach-Zehnder interferometer, I'll see the same interference pattern. It doesn't know the difference between those. It just measures the spectrum. Okay? Now, this is where a lot of the controversy came from. Is that all there is to it? Is the only thing that distinguishes one kind of light from another is its spectrum? And the answer is no. This has only to do with, because we were measuring, just counting them individual photons, one at a time. And so this has nothing to do with the distribution, the probability distribution of photons. It has only to do with the mean number of photons. And two sets of fields which have the same numbers of photons in each mode will exhibit the same photon count of this sort, if all we're looking at is the mean number of photons. But something's different when we start thinking about Hamburg Brown and twins. So now, let's talk about Hamburg Brown and twins. Firstly, we no longer have a single photodetector. We now have two. Okay? So here's a new experiment thought of from the quantum mechanical point of view. I have two photon counters. They each count photons. And now I'm going to delay this by some amount tau and put it into a coincidence counter. So this coincidence counter asks for the joint probability that two photons came, one photon at, say, time 0 at this detector, and one photon at some delayed time, or advanced time, depending on the sign of this, tau, okay? So it's looking at coincidences of two photons, two photon events, rather than individual photon events happening in one photodetector, okay? What is the quantum mechanical theory tell us that should be equal to? How should we get that coincidence rate? Is it just equal to the product of the two intensities? Well, you might think, but so let's think about this. What's happening here is let's just imagine the microscopic. We have some atom here that's going to be ionized, right? The photon's going to come in here and cause this photoelectron to be. And at the same time, we want that to happen. So we have to look at Fermi's golden rule, where we have now two atoms, both in the ground state, as part of my initial state. I have some state of the field initially. So this is my total initial state. And then my final state is both in the excited state and some final state for the field. Now what am I going to put in between here to get me from here to here? It can't be just one of my d dot e's, because that only can correspond to single photons. This is a two-photon effect, right? So this is a second order in perturbation theory effect. This is not a first order, this is a second order in perturbation theory. So I need to look at two powers of the interaction Hamiltonian in order to get there, right? When I do the expansion of the time evolution operator, which has the exponential of the Hamiltonian, there are terms that are quadratic. They're the second order terms. And there's, proportionality constant here, and this thing gets squared. Now, of course, this thing has d dot e's in it. And E is the superposition of E plus and E minus. But if I'm going to get from the ground state to the excited state in both of them, then both of them have to come from the E plus terms in the rotating wave approximation. So, in the same way that we did this for the single photodetector, now for the two photodetectors, this thing is going to be proportional to E plus at doesn't matter if it commutes, but okay. So there's some atom that gets ionized here at position 1 at time t1. There's another atom that gets ionized at position 2 and time t2. And my rate of coincidence will be proportional to this. Okay? Again, when I sum this over, because I don't actually measure all the final states of the field, I trace over that. So then I write this times its conjugate. See that? And then I sum over that. What do I get? I'll do it again. You take this and you conjugate it. And then you sum over the intermediate states.
Oh, I know.
Well, every time I conjugate, an E plus becomes an E minus. So this just becomes the expectation value over the initial state of the field. Average over the interfield. Yes, sir.
Why don't we simply get the product of the intensities?
Good question. What do we get? What we get is the expectation value of the product of the intensities. It's an excellent question. But normally ordered. And this is truly important. So this double dot symbol, which I'm having a hard time drawing because I never leave enough room at the edges of the border. Let's try again. Equal. So that's what that equals. What do I mean by that? So what is the product I at R2 T2, not times Ri going T1? What is that product? Well, that is equal to E minus E plus at time So this is I2, right? Times E minus at R1 E plus at R1. That's what the product of the intensities is, right?
You
But
have-
that's different.
is that-
They're not the same. Why? These don't commute. E minus and E plus don't commute. One has A pluses, A daggers, and one has B's. The double dot here means the following. Close your eyes and pretend they commuted. Move all the guys that have the daggers, put them on the left. And all the guys that don't have the daggers, put them on the right. So the normally ordered version of this is march all the guys E minuses to the left and march all the E pluses to the right. Now classically, this wouldn't have made a difference. These guys would be equal classically, because classically, E and E star commute. They're just numbers. But quantum mechanically, they don't. So what is true is that the joint detection rate or probability is not equal to the product of the intensities. It's equal to the product of the normally ordered intensities, and that's going to be important. And that came out of what we just did from Fermi's golden rule. That there was the processes that led to photon counting were the ones associated with two absorption events. So they had these two E pluses here. And not an E plus and an E minus. And then when we conjugated, we got this. All right. Yeah.
So do the colons indicate we can't change the order, or because you have the colons on?
The colons on mean you can change the order however you like.
Okay.
That's what it means.
Okay.
That's just, it's just a notation.
Okay.
So normally ordered A, dagger A, dagger A is equal to A dagger squared, A squared.
Ah, okay. Okay.
That's what that means. All right. So now that we have this formalism, we can calculate what we expect quantum mechanically in the Hanbury-Brown twist experiment. This is equal to this. Okay. Now again, when expressed in terms of coherent states, by the way, this is known as G2 of tau, little big G2. Okay? Little g2 is equal to g2 of tau divided by the average intensity squared. This will have a physical interpretation, as we'll see in a moment, in terms of photons. In terms of classical amplitudes, this has exactly the same form as before. Because this is normally ordered, and because all of the annihilation operators, or positive frequency components, are on the right, and all the negative frequency components, or creation operators, are on the left, what happens when I take the expectation value of this with respect to a coherent state?
You get zero.
No, I don't.
Oh, wait a minute, okay, because
It's a coherent state.
Oh, so no, you don't get zero, because
What do I get?
You get the same.
intensity squared?
I get exactly the classical value, right? Because if I take this with respect to the classical amplitudes, I get exactly, so that's why it has to be this way. This is what Glauber noticed. In fact, it will always factorize. If I have an n photon photodetectors, I have n E pluses and n E minuses.
But if you have a Fock state, that's when you...
Yeah, that would be different.
Okay.
So the quantum theory recovers the classical theory if the state is a coherent state, or a classical statistical mixture of coherent states. Because then I would just take my expectation value of the coherent states and average it over the classical probability stream. It would be exactly the same as we hope. So that's nice. The quantum theory recovers the classical theory when the state is classical. It's a classical statistical mixture of coherent states. But how do we understand this now in terms of photons? We're going to preview this right now. I'm going to finish till the very last lecture of the semester, but that's okay. It's good to have something good to finish on. But let's just get started on this. Let's look at just to get started here, let's look at tau equals 0. Okay, tau equals 0 is the case where I'm looking at, I have two detectors, and I want to know what's the probability for both to go click at the same time. Okay. Exactly the same time. So what it's looking at is there are some two photons that are in this time interval. And it wants to know what's the probability that I'll have two photons in that short time interval. Okay? As seen by one photon goes here and one photon goes there. So it's looking for both photons there to be sort of a probability for there to be two photons in that time window. One that lands on detector A and one that lands on detector B. So we can, according to that, this thing is equal to this. Right? Now, this is all, I can think about this as a kind of single mode deal. So this is equal to that. Okay? For that one mode. Let's take a look at that. Let's write that in the number basis. Oh, no. Hold on a second, I want to just think about one thing here. Okay, so this is equal to, I'm going to write this one. So I might have some mystical mixture, might be a pure state, I'm not saying. Okay? There's some, this could be a single pure state, this case I have some single phi, but now I might have some mystical mixture. Now, let's take this and substitute in a complete set. Okay? Then, this is equal to the following. Right? So my joint, the probability of seeing these two photons, one at this detector and one at this detector, is given by this expression. Now, what happens when A hits N on the left? It raises it, right? And I get a square root of N plus 1. And then I raise it again. I get a square root of N plus 2, right? So this will be equal to N plus 1 times N plus 2 times N plus 2. So this is equal to the probability of seeing N plus 2 photons given that the state was psi. Right? And then I have to average over all possible psis. Okay, now let's just complete this lecture by asking the following thing. Suppose that this light that came in here was had a weak intensity. Suppose that suppose that the mean number of photons is much, much less than 1. Just think about that case first. Okay? Then the dominant term here is the case, I mean, there's very few photons. Maybe I'll see 2, but I'm not going to see, that's going to be much bigger than 3 or 4 or 5, right? So this is then approximately going to be equal to the case, the smallest number, this is the sum over n, by the way. I left that out, that's important. The smallest case where n is 0. So this is approximate that says that the joint probability of finding these two photons is approximately equal to 2. So n is 0, n is 0, 2, times the sum over all phi, the probability of having phi, times the probability of seeing two photons giving. So this is the probability of finding two photons. Now here's the rub. The rate at which I see this, or the probability of seeing these two detections, is twice the probability of seeing two photons. It's not equal to the probability of seeing two photons. It's twice the probability of seeing two photons. Why?
Is it that uncertainty that you talked about before, the fluctuations?
Well, even if I had, let's suppose the state had exactly two photons in it. Suppose there were exactly two photons.
Because you're double counting?
I haven't double counted anything. This is actually the case. In fact, this is related to the fact that in the Hamburg-Brown twist experiment, this is I squared, but this is twice I squared. The reason reason is that there's two photon interference. There are two different paths that can lead to this coincidence. What are they? Well, this photon can go like this, and can go like that. Or this photon can go like this, or that one can bounce off. So there are two paths, and they interfere. This is an example of two photon interference. And as I said, there was all this confusion. How can you possibly have this hamburger ground twist experiment when every photon only interferes with itself? Well, that's just not right. When you have a single photon counter, like in a Mach-Zehnder interferometer, well then indeed, it's only a single photon, and no two photons are interfering with each other. But when you have a two photon event, two clicks in two detectors, or it could be in the same detector, but two different clicks, and there are two different histories that can lead to them, well then they interfere with one another. And we see this here came from the fact that when we did this square root, we get the we have the statistics that a dagger acting on n is the square root of n plus 1. N times n plus 1. This is what's sometimes known as Bose enhancement. That is to say, two bosons are more likely to be in the same mode than for distinguishable particles. This came from the commutation relations of A and A dagger. If these were fermions, we wouldn't see this. We would see there couldn't be two particles in the same mode. And not only can there be two particles in the same mode, but it's more likely to have two in the same mode than have two in separate modes. Now, final question to leave you with that we'll finish up completely for next time. This twice factor then, saying there's more likely to be two photons arriving at the same time than if they were just independent. But if this was a coherent state, if this wasn't thermal light, this would be just flat. Well, I'll let you think about that, and we'll pick that up next time. Very good.